Yang LeCun just published a new paper. Using computer-verified math, he did what few in AI have achieved, proving that AI's world understanding doesn't depend on data volume or computing power. It only depends on what method you use to train it, and the kind of method that can succeed, he proved, is almost the only one. This might sound ordinary, but what he's actually challenging is the core belief of this current wave, the belief at the heart of large models, that brute force leads to miracles. Everyone is competing to see who has more data, more powerful computing, and bigger parameters. So Yang Li Kun's paper basically told everyone right to their faces that you're all heading in the wrong direction. This video might be a bit abstract, but it's important for everyone to get a sense of the latest technical directions. I'll try to explain in plain language just how significant this verification is. They put the entire proof into a proof assistant for coaches, which is a tool mathematicians use to check whether a proof is correct. Even Terence Tao's grand theorems use it, and if you skip a single logical step, it immediately throws an error. But the 5 theorems in this paper had 0 errors. So what exactly did they prove? Let's talk about that first. One key term is world model. If you look at the first figure in the paper, it's really intuitive. On the far left is how the real world actually looks, a bunch of clean, non-interfering variables. You can think of these as things like the position of objects, their speed, color, lighting, each one clearly responsible for a single aspect. The middle part is the data our eyes actually see. These variables get tangled together by a complex process, turning into a chaotic mess. Visually, it's like a colorful, twisted spiral all tangled up. What AI needs to do is unravel this mess in the middle and restore it to its original, organized state. Restore it. Restore it to that clean state on the far left. If it can untangle the mess, and the way it does so is especially simple, that means the AI has truly learned the ability to build a world model. This is called linear identifiability. In plain language, it means the world map in your mind is only different from the real world via rotation. There's no distortion at all. So how does this method, called LEGPA, achieve that? To put it simply, it comes down to 2 steps. The first step is called alignment. You forcefully align 2 different views of the same thing. For example, in a video, you tell the model that 2 adjacent frames are actually the same thing. The second step is to force all the features output by the model to line up in a specific shape, a Gaussian distribution. What's a Gaussian distribution? It's the famous normal distribution, that bell-shaped curve where most cases cluster around the average in the middle, and the more extreme cases are less common and fall toward the edges. For example, if you plot the heights of all the students in a class, a group's weights, or test scores, you'll usually get this kind of curve, high in the middle and low on both sides. It's the most common and unbiased distribution in nature. And the most groundbreaking part of Yang LeCun's paper is right here. The only distribution that can guarantee AI can fully reconstruct the world is the Gaussian. There's nothing else like it. If you switch it to another shape, like one with both ends raised or a flat one, the reconstruction immediately falls apart. In their experiments, when they shifted the distribution from one end to the other, the accuracy of the reconstruction peaked sharply right at the Gaussian point, but dropped off on both sides. As for how he proved that it must be linear and must be Gaussian, the approach is actually quite straightforward. They broke down any function learned by the AI into straight parts, parts that bend once, parts that bend twice, layer by layer. Then they discovered a hard rule. The model didn't add even a bit more bend inside. If there was even a little extra bend, the score would be strictly deducted a bit, until it was linear with the least deduction, so the optimal solution was forced to be linear. There's also a particularly ironic point here. In classical signal separation theory, Gaussian is the only distribution that causes separation to fail. It's the unlucky one everyone tries to avoid. But in Yang LeCun's new framework, Gaussian is precisely the only one that allows separation to succeed. The same Gaussian that was a terminal illness in the old theory has become the cure in the new theory, but just proving it on paper wasn't enough. They actually tested it on a real robotic arm with 2 joints. In the map learned by the AI, they drew the straightest possible line from the starting point to the target. Then they had the robotic arm follow that path, and when they decoded it back into the real world, the robotic arm also moved in a beautiful straight line. But if you use an encoder that hasn't learned the world model well, and give it the same straight line command, the robotic arm moves in a wobbly, crooked way. So is this all just hype? Not really. They honestly admitted a major limitation. If the data comes from a purposeful strategy, for example, if the robotic arm is specifically trained to reach for a fixed target, then its distribution is no longer Gaussian, and this guarantee immediately fails. So, to keep the theory valid, AI should explore as randomly and broadly as possible during self-learning, without too much purpose or direction. That brings us back to what was said at the very beginning. The large model approach relies on brute force to achieve miracles. The more data and the more computing power, the closer we get to intelligence. Yang LeCun's main point in this paper is that direction beats brute force. There's one specific line that really stuck with me. Whether AI can truly learn depends on two things: the world's nature and your methods. These two factors basically decide everything. It has nothing to do with how much data you pile up. This time, he's no longer just the guy who keeps saying that large models are a dead end. This is the first time he can actually present a mathematically verified zero-flaw result. This math tells you that the world model approach isn't just a matter of belief, it's a theorem. Of course, this only proves half of it. What he proved is that if the world is Gaussian, then AI will definitely be able to learn it. But as for whether the real world is actually Gaussian, even the paper admits that just looking from the outside, you'll never really know. So with this lock, he managed to pry it open with mathematics. There's just a crack. What's behind the door? We'll have to wait and see as things unfold. That's all from me. Follow me, and I'll see you next time.